compact toroid formation, compression, and acceleration. J. H. Degnan, R. E. Peterkin Jr., G. P. Barker, J. D. Beeson D. Bell, M. E. Dearborn D. Dietz, M. R. Douglas S. E. Englert, T. J. Englert K. E. Hackett, J. H. Holmes, T. W. Hussey, G. F. Q2 F. M. Lair, G. J. Marklin B. W. Mullins, D. W. Price, N. R. Roderick, C. L. Rudin, C. R. Sovinik, and P. J. Turchel High Energy Plasma Division, Phillips Laboratory, Kirtland AFB, New Mexico 87117. G. Bird and K. Coffey and S. W. Seiler Physical Sciences, Inc., Alexandria, Virginia 22314, Y. G. Chen, D. Gale, J. D. Graham, M. Scott, and W. Somers Maxwell Laboratories, Inc., Albuquerque, New Mexico 87106, received December 4, 1992, accepted March 15, 1993. Research on forming, compressing, and accelerating milligram-range compact toroids using a meter diameter, two-stage puffed gas, magnetic field-embedded coaxial plasma gun is described. The compact toroids that are studied are similar to Spherimax, but they are threaded by an inner conductor. This research effort, named Marauder, Magnetically Accelerated Ring to Achieve Ultra-High Directed Energy and Radiation, is not a magnetic confinement fusion program like most Spherimac efforts. Rather, the ultimate goal of the present program is to compress toroids to high mass density and magnetic field intensity, and to accelerate the toroids to high speed. There are a variety of applications for compressed, accelerated toroids, including fast-opening switches, X-radiation production, radio frequency, RF, compression, as well as charge-neutral ion beam and inertial confinement fusion studies. Experiments performed to date to form and accelerate toroids have been diagnosed with magnetic probe arrays, laser interferometry, time and space, resolved optical spectroscopy, and fast photography. Parts of the experiment have been designed by, and experimental results are interpreted with, the help of two-dimensional 2D, time-dependent magnetohydrodynamic (MHD) numerical simulations. When not driven by a second discharge, the toroids relax to a Walcher-Taylor equilibrium state that compares favorably to the results of 2D equilibrium calculations and to 2D time-dependent MHD simulations. Current, voltage, and magnetic probe data from toroids that are driven by an acceleration discharge are compared to 2D MHD and to circuit solver slug model predictions. Results suggest that compact toroids are formed in 7 to 15 MSE and can be accelerated intact with material species the same as injected gas species and in trained mass greater than 1/2 the injected mass. First introduction. The compact toroid, CT, is an axisymmetric toroidal plasma confinement system which was first discussed as a fusion concept in 1958 by Alf N. Two types of CT plasmas are discussed in the literature. Experiments which form a configuration with null toroidal field, called a field-reversed configuration, FRC, of which the field-reversed experiment, FRX, effort at Los Alamos National Laboratory, LANL, is an example, are generally prolate theta pinches in the presence of a reversed bias magnetic field. Configurations with non-zero toroidal fields, called Spherimax, have been produced in the first paramajor Leuven to 13 Netix Spherimac, PS1, the compact torus experiment, CTX, 14.1 $5 11,617 and Beta 2 efforts at the University of Maryland, LANL, Princeton University, and Lawrence Livermore National Laboratory, LNL, respectively. The compact toroids that are discussed herein are of the Spherimac variety. A potential advantage of the CT as a fusion reactor is the relative simplicity of the design, for example. Neither conductors nor vacuum chamber walls are required to pass through the hole in the torus. The interest in compact toroid plasmas, however, transcends their possible usefulness as alternate magnetic fusion devices. For example, as proposed in the LNL ring accelerator experiment. RACE, Project 19, which grew out of the Beta 2 effort, compact toroids can be used as hypervelocity projectiles, as producers of soft X-rays 20.210 G, as fast-opening switches for electrical power amplification. 22 to 24, These alternate ideas involve translation of the rings to regions far from the region of formation, and possibly acceleration of the rings to high speed. Achieving this is made possible by reintroducing a center conductor that does pass through the hole in the torus. While the physics of these objects is essentially the same as for the spheromac, the name compact toroid is at present used for a spheromac that is threaded by an inner conductor. The Phillips Laboratory Marauder, magnetically. Present address, White House Office of Science and Technology Policy, Washington, D.C., 20,500. Present address, European Office of Aerospace Research and Development, London, England. Permanent address, the University of New Mexico, Albuquerque, New Mexico 87,102. Present address, the University of Wisconsin, Madison, Wisconsin, 53,706. Permanent address, the Ohio State University, Columbus, Ohio, 43,210. 2,938. Phys. Fluids B58, August 1993, 0899 to 8,221, 93. 58, 2,938, 21sts, $6. 1993, American Institute of Physics. 2,938. Accelerated ring to achieve ultra-high directed energy and radiation. Compact toroid program is studying the formation, compression, and acceleration of magnetized plasma rings. The compact toroids are produced in a magnetized coaxial gun. In that respect, they are similar to the CTX, Beta 2, and Race spheromacs. In fact, the present effort is a larger size and energy variant of the Race compact toroid program, and was inspired by it. The ultimate goal of Marauder is to accelerate a 0.5 to 2 milligram mg CT to a kinetic energy level of a few mj using a 5 to 10 mj coaxial gun discharge. The approach is to use the first stage of a meter diameter, two-stage puffed gas, magnetic field embedded coaxial plasma gun discharge to form a CT. The second stage discharge may be used to compress and to accelerate it. Initially, a controlled amount of neutral gas and a specified amount of poloidal magnetic flux are injected into a coaxial plasma gun. The thirst, or formation, discharge ionizes the gas puff and creates a toroidal magnetic field that pushes the plasma and initial poloidal field downstream, forming a magnetic field embedded plasma ring. Under sufficient pressure from the toroidal field, the injected mass and entrained poloidal field balloon out into a coaxial expansion volume at the muzzle of the formation gun, and a toroidal magnetized plasma bubble is formed. The initially poloidal magnetic field lines are stretched and are given a twist by the toroidal field from the formation discharge. As occurs in related gun-based spheromac experiments, the stretched helical magnetic field lines reconnect 9.30 at the neck of the toroidal bubble, which is near the muzzle of the plasma gun, on a timescale that is short compared to that of classical diffusion. Thus is formed a toroidal plasma with non-zero magnetic helicity, that is with closed poloidal magnetic field lines linked with closed toroidal magnetic field lines. The magnitude of the poloidal and toroidal components of the magnetic field are comparable. After reconnection, the magnetic field distribution of the plasma ring relaxes towards a force-free configuration of non-zero magnetic helicity called a Walcher-Taylor WT state. 3 to 4. When in the WT state, a compact toroid is stable to resistive and ideal MHD instabilities and can have considerable stability under acceleration by magnetic pressure, provided that the accelerating field or piston field is less than the CT self-magnetic field. In the Marauder experiment, the acceleration field is a toroidal field provided by the second stage plasma gun discharge. One possible full energy design that employs the 1300 mF 9.36 mJ Shiva Star fast capacitor bank at the Phillips Laboratory is illustrated in Fig. 1. In this design, the toroid is formed by the first of two discharges in the gun and expansion volumes that are shown in the bottom half of the figure. The expansion volume traps the magnetic flux and is the place in which the plasma relaxes to a nearly force-free equilibrium. The second discharge pushes the CT downstream, out of the expansion volume. An energetic acceleration discharge is expected to be able to compress a CT between the converging electrodes of a pair of nested cones with a common focus, increasing its mass density. Fig. 1. Marauder High-Energy Compact Toroid Accelerator Design Concept. A compact toroid is produced in the plasma gun and expansion volume that form the lower half of the apparatus. The toroid is then compressed between a pair of converging electrodes and accelerated in the converging coaxial gap downstream of the compression cones, and magnetic field strength in the process. During compression, magnetic energy is accumulated upstream of the CT in an inductive store. After compression, the energy in the inductor can be used to accelerate the toroid to high speed, greater than 1,000 km (SEC). In this paper, we describe the Marauder concept and a particular CT formation, compression, and acceleration configuration that has been studied via experiment and numerical simulation. In SEC 2, Experiment, we discuss the experimental design and follow this with the relevant theoretical models for an equilibrium CT in the present coaxial geometry in SEC. Third, Equilibrium. Experimental diagnostics are described in detail in SEC. Fourth, the dynamical approach to equilibrium for a gun-produced CT in a coaxial flux conserver and two-dimensional, 2D, timer-dependent magnetohydrodynamic, MHD, numerical computer simulations of the formation and acceleration of the CT with a straight coaxial accelerator segment are discussed in SEC. Fifth, experimental results of formation, compression, and acceleration experiments are presented in SEC. Sixth, our conclusions are given in SEC. Seventh, second, experimental design. Two existing experimental configurations are illustrated in Figure 2. In both designs, the formation gun forms the lower portion of the apparatus and has inner and outer radii of 44.77 and 52.39 centimeters, respectively. This creates an electrode gap of 7.62 centimeters. 3 in. The inner electrode is the anode, and the first stage discharge is applied across an insulator that is located at the bottom of the gun. The coaxial expansion volume is attached to the muzzle of the gun and takes the place of the flux conserver of other. 2939. Phys. Fluids B. Vol. 508. August 1993. Degnan et al. 2939. B. Fig. 2. 2. Existing experimental Marauder designs. Results from the straight coaxial geometry above, A, are discussed in this paper. The converging electrode geometry below, B, is a step towards the full energy design of Figure 1. Spheromac experiments. Its purpose is to trap the magnetic field lines, hence it is sometimes called the trapping volume. For the design on the top, Figure 2, A, a short cylindrical acceleration coax is placed downstream of the expansion volume and forms the upper portion of the apparatus. In the design on the bottom, Figure 2, B, the cylindrical acceleration coax is replaced by a compression section that is formed by a pair of nested cones and a cylindrical acceleration coax with a mean radius that is 1/3 that of the expansion volume. Whereas the straight coaxial design, Figure 2A, is limited to operation at lower accelerator bank energy, it affords greater diagnostic access to the early stages of CT formation. It also allows easier comparison between experiment and theory. The recently fielded compression design enables operation at higher energy and is a significant step toward the full energy goal. This design enables easy change of the conical compression and downstream acceleration electrode hardware. The present paper focuses on the straight coaxial geometry of Fig. 2A. In addition to the relatively fast, energetic formation and acceleration discharges, the experiment requires a pair of slower low-energy discharges for magnetizing the gun and injecting mass into that volume. The initial bias magnetic field is injected by a 10 millisecond MSE rise time 15 mF 1.5 to 2 kV capacitor. Fig. 3. Initial bias magnetic flux distribution as computed from currents in the field coils in the experimental geometry. The geometry corresponds to the right-hand side of Figure 2A, discharge through a pair of solenoids. the total field injection circuit inductance for both coils, with series connection and azimuthal current in the same direction, is measured to be approximately 4 mH. The total resistance is approximately 85 m. The peak solenoid current is 3 Ka at the maximum into the discharge for a 2 kV initial capacitor voltage. The maximum value of the radial component of the magnetic field within the formation gun volume is in the 0.10.2 T range at 12 MSE. The delay is caused by the magnetic diffusion time through the electrodes and support structure. The bias field diffusion time through the electrodes is sufficiently long that Bn, bias, and may be used as a time-independent boundary condition on boundaries with unit normal, n, during the 10 to 100 MSE timescale of the plasma experiment. A magnetic diffusion code is used to calculate BIS, Vibius x6, r, where is a unit vector in the direction of the azimuthal coordinate by integrating Debian, di a bias, m-o, where n is the electrical resistivity, 40 is the permeability of free space, and A is the differential operator, R, A, plus, in time from 0 to 11.8 MSE, the time when the formation bank is fired. A finite difference version of this equation is solved on a grid in the cylindrical RZ plane, with all of the conducting components of the experiment included. The code computes the diffusion of the magnetic field generated by the bias coils through these components with the current in the bias coils specified to be I, T, equal to I1 sin 20th msec. Figure 3 shows a contour plot of with Joe 26 Ka. The symmetry axis is always vertical, and only the portion of the RZ plane that lies to the right of the axis is 2940. Phys. Fluids B, Vol. 508, August 1993. Degnan et al. 2940. Fig. 4. Radial and axial components of the bias magnetic field as functions of T near mid-gap. Points represent measured values and the lines are values computed with the diffusion code. B, solid line and diamonds, B, dashed line and plus signs. Displayed in subsequent figures. In order to check the results of the diffusion code, auxiliary experiments were performed using only the bias coils with a peak current of 3.8 Ka. And the magnetic field was measured with Hall magnetic probes. Figure 4 shows a comparison of the field components B and B to measurements made at mid-gap in the gun as a function of the axial coordinate, Z. The slight discrepancy is probably due to a small amount of paramagnetism acquired by some of the stainless steel components during fabrication, which was not taken into account by the computer code. Between 1 and 2 mg of gas is injected into the coaxial gun using a circular array of 60 fast gas valves through the 52.39 cm radius outer electrode. The puff valve array is driven by a 480 pf, 5 pH, 3.5 kV capacitor discharge through a series parallel array of fast valve pulsed solenoids. Transient gas distributions have been measured in situ with Penning ionization gauges and with piezoelectric pressure probes. More detailed auxiliary experiments have been done that carefully measure the total mass that is injected from a single valve as a function of time. These auxiliary experiments employ a theta discharge to drive the fast closure of a copper injection tube. 36. The total mass from a single valve has been measured as a function of time for a particular set of values for the puff valve pressure and time delay. The results, multiplied by 60 to account for the 60 valves in a marauder experiment, are shown in Fig. 5. The data points are fit to a function of the form 636.3% pressure. Of the valve of cross-sectional area, A was also measured and was found to be equal to the room temperature sound speed. Use of the continuity equation, dm dt equal to POA, then allows the time-dependent mass density, P, to be computed at the exit where m equal to OL28. 5 m pros A equal to 35.71. And to equal to PSE for argon puffing with 100 POIA A valve plenum, the velocity of the gas, 2, flowing out. Fig. 5. Injected argon mass versus time, from the 60 gas injection nozzles. Points are experimental, and the curve is a best fit to the data if the rogue point at 710 psi, 0.4 milligrams, is ignored. To the valve. This information is used to specify a time-dependent boundary condition for calculation with a 2D MHD code, MARCHs, which is discussed in some detail in SEC 5th. The boundary condition mimics the conditions at the end of the nozzle. The code then computes the axisymmetric time-dependent spatial density distribution for a single nozzle. The initial mass distribution in the Marauder formation gun
The idea that empty space isn't actually empty,
valves.
that it's a
Although
roiling,
this superposition
energetic
is truly
sea called the
three-dimensional.
quantum vacuum.
To the valve. This information is used to specify a time-dependent boundary condition for calculation with a 2D MHD code, MARCHs, which is discussed in some detail in SEC 5th. The boundary condition mimics the condition. Points are experimental, and the curve is a best fit to the data if the rogue point at 710 psi, 0.4 milligrams, is ignored. To the valve. This information is used to specify a time-dependent boundary condition for calculation with a 2D MHD code, MARCHs, which is discussed in some detail in SEC 5th. The boundary condition mimics the conditions at the end of the nozzle. The code then computes the axisymmetric time-dependent spatial density distribution for a single nozzle. The initial mass distribution in the Marauder formation gun is a superposition of the distributions from the 60 gas valves. Although this superposition is truly three-dimensional, the number of injection valves is chosen to be large in the hope that the superposition is not a strong function of the azimuthal coordinate. 6. The superposition of 60 mass distributions is then averaged over 6 to obtain a mass distribution that is a function only of the two poloidal coordinates, r and z. The resulting 2D mass distribution is displayed in Fig. 6, where isocontours of the heavy particle number density are shown in a cross-section of the coaxial gas gun. In this figure, the contour labelled J represents the largest heavy particle number density of 1016 cm to 3, and is enclosed by the I contour which surrounds the point at which the gas injection nozzle intersects the formation gun. The formation discharge is applied at the bottom of the gun. This density distribution is used as the initial state for the 2D MHD simulations of the time development of the CT that are discussed in SEC. 5th, the formation discharge is typically driven by a 110 UF 70 kV capacitor bank. The current rises to approximately 2.4 megaamperes in 3.25 pse. The formation capacitor bank consists of 3 Shiva star-type modules. The acceleration discharge is driven by part or all of the 36 modules of the Shiva star bank, which has had its charging and triggering reconfigured to allow the use of 3, 6, 12, or all 36% of its modules, thus permitting the capacitance to be varied between 110 and 1300 pf. The acceleration bank voltage can be varied from 40 to 120 kV, and is typically set to 80 kV. The inductance of the acceleration bank can also be varied by thickening sections of the parallel plate transmission line. Though the Shiva star bank and transmission line can have an inductance as low as 3 Nh, the discharge. 2941. Phys. Fluids. B. Vol. 5. No 8. August, 1993. Degnan et al. 2941. Fig. 6. The axisymmetric heavy particle number density that is obtained by averaging the superposition of the mass density from 60 gas valves. There are 10 isocontours that are logarithmically spaced with 2 contours per decade between A at 1 times 10 cm and J at 5, 0 times 100 and 1 em. The J contour is inside the I contour, which is at 1 x 10. Inductance, including the second-stage coaxial gun, is typically between 60 and 70 Nh when it is used to accelerate compact toroids. The choice of accelerator bank capacitance, inductance, and voltage is dictated in part by the desire to prevent the toroidal acceleration magnetic piston field from pushing past the compact toroid and running downstream ahead of the CT. This phenomenon, termed blowby, 38% generally occurs when the magnitude of the acceleration field exceeds the magnitude of the poloidal field of the CT in the neighborhood of the electrode wall. The accelerator circuit parameters, including charge voltage, the initial CT parameters, including mass, field strength, major and minor radii, and coaxial accelerating electrode geometry all affect the ratio of the piston field to the CT self-field. The ratio of the accelerating field to the CT self-field may be kept below unity by adjusting several parameters either unilaterally or in combination: higher initial bias field, more abrupt compression, lower acceleration bank voltage, or a high acceleration inductance. The acceleration discharge, which is applied through a circumferential feed slot in the outer electrode near the muzzle of the formation gun, injects toroidal flux inward in a manner that encourages the reconnection of poloidal magnetic field lines. The behavior is similar to that achieved with a pinching coil discussed in Ref. 18. It then lifts the toroid upward and drives it downstream, in the process performing work on the CT third equilibrium theory. As in a spheromac, the CT magnetic fields are generated primarily by internal plasma currents. In the absence of external magnetic field generating sources, the magnetic field distribution of a CT depends only on the geometry of the confining electrodes, which is sometimes called the flux conserver. However, any magnetic flux that penetrates the flux conserver as a consequence of nearby external currents will also affect the CT self-field distribution. The magnetic field distribution in a magnetized gun discharge relaxes towards a minimum energy equilibrium state in which the magnetic helicity is non-zero. The magnetic helicity, a conserved quantity in ideal MHD, is a measure of poloidal and toroidal magnetic flux linkage and is defined as K Jax-B dV, where the magnetic field is derivable from a vector potential, B Vxa. This equilibrium is called the Walcher-Taylor WT state. 31 to 34. In a closed system, the WT state is force-free, Jxb, Vp equal to 0, where J is the current density, which in SI units is equal to Vxb, H, and P is the thermodynamic plasma pressure. As a consequence, Vxb equal to AB, with the constant ratio between the current and the field, A equal to μj B. When integrated over a surface area, A is also proportional to the ratio of the poloidal current to the poloidal magnetic flux, or equivalently to the ratio of the toroidal current to the toroidal flux. In a cylindrical orthonormal basis, R, Z, an axisymmetric solution to the force-free equilibrium equation in an annular region, which is defined by both inner and outer conductors of fixed length, in which the poloidal magnetic field is everywhere tangent to the boundary, and in which the toroidal field vanishes at the boundary, is 21.4. B, 22.1 half bow, 1 plus COs K, ZO. X, J1, R plus FN1, R. 23 to 12B plus Shui, Sin, K, Z, Zo. X, X, Yo. J1, AR plus FN1, AR, where Jo and J1 are Bessel functions of the first kind, No and N are Bessel functions of the second kind, and 22 are 2, K2 where K is the axial wave number. The multi. 2942. Phys. Fluids B. Vol. 508, August 1993. Degnan et al. 2942. Plyer, F. is entirely determined by the boundary conditions. The boundary conditions at and out further imply that J1, 2, N, route, J1, rho, N1, A equal to 0, where the ST@0 of this cross product of Bessel functions has an asymptotic expansion. For the expansion volume of figure 2, A, 0.4% 477 meters, and Fout equal to 0.6255 meters, and a 15.38 meters. The effective height of the cylindrically symmetric coaxial flux conserver, AZ, is 0.2036 meters. The demand that B vanish at z equal to zo and zo plus as implies that km and m, AC for integer m, for the lowest mode, k equal to 15.43 meters. As a consequence, the eigenvalue annular minus 21.78 for a simple annular flux conserver of these dimensions. The true geometry of the Marauder formation experiment, however, is only approximately annular. Axisymmetric solutions to EQ 3 in the experimental geometry are computed by solving the Grad-Shafranov equation, A equal to A IC plus A, where is the poloidal flux function, which is related to the magnetic field by and IP is the total current linking the toroid and passing through the flux conserver in the poloidal direction. A finite difference version of the Grad-Shafranov equation is solved using the conjugate gradient method on an axisymmetric RZ grid with a staircase boundary that approximates the actual experimental configuration. If the bias field is 0 and there is no flux conserver current, IP 0, then EQ 3 is homogeneous. In this case, the solution to EQ 3 depends only on the geometry, and A is an eigenvalue equal to 22.35 meters. This is called the homogeneous solution, has no field lines penetrating the walls, and may be freely translated. A contour plot of the flux function for this solution is shown in Figure 7. If the bias field is included in the calculation, or if there is an external toroidal flux due to a flux conserver current, then EQ 3 is inhomogeneous and has solutions for all values of A, hence A becomes a continuous parameter. Minimum energy states with the correct bias field boundary condition can therefore be computed as a function of A and IPC. Figure 8 shows a sequence of minimum energy states with increasing values of A and I0. The amplitude of the magnetic field is a monotonically increasing function of a going from the bias field level at a 0 to infinity at A 22.35 meters, the eigenvalue of the homogeneous case. The A value in the experiment will therefore always be less than this eigenvalue and will have to be determined by fitting to the data. The preceding axisymmetric solutions are only guaranteed to be local minimum energy states. To guarantee complete stability, they must still be shown to be global minimum energy states. This requires showing that the non-axisymmetric or helical minimum energy states have a higher energy. Non-axisymmetric minimum energy states are computed by solving Vxb, a Bm assuming Bem with m plus 0. This eigenvalue equation is also Fig. 7. Walcher-Taylor equilibrium state of the poloidal magnetic flux in the geometry of Figure 2. A, solved using the conjugate gradient method, with the same mesh as before with B. N0 on the boundary, since there are no externally applied helical fields. The energies of these helical states are proportional to the eigenvalues. M, therefore the axisymmetric state, is stable if it's AAM for all M. The lowest energy helical state has been found to be the M6 solution, with a 29.3 meters. Since the axisymmetric minimum energy states always have a less than 22.35 meters, they are thereby guaranteed to always be stable for the experimental configuration discussed herein. Furthermore, since the margin of stability is so wide, it is likely that any similar flux conserver configuration will be stable as well. Relaxation towards the WT, or minimum energy, state is generally observed to take place on a timescale shorter than the resistive diffusion time, 17.18, and such is also the case in Marauder. When in the WT state, the compact toroid is stable to ideal and resistive MHD instabilities, when subsequently accelerated by magnetic pressure from 2943, Phys. Fluids, B. Vol. 5. No. 8. August, 1993. Degnan et al. 2. Fig. 8. A sequence of minimum energy states in the experimental geometry for 7 different values of the continuous parameter, A for cases in which magnetic flux penetrates the gun walls but with I equal to 0. The WT state, it is resilient and can have considerable stability, provided the acceleration field, or magnetic piston field, is less than the compact toroid self-magnetic field. Considerable detail on field distributions and stability against tilting for toroids in a coaxial geometry is given by Izuka et al. 42. Fourth diagnostic description. The The diagnostics for the Marauder experiment include Rogowski coil belt, current probes, and capacitive divider voltage probes outside the vacuum system. Few turn 0.2 to 0.8 cm2 inductive magnetic probes that measure azimuthal, radial, and axial field components at numerous and adjustable locations in coaxial discharge geometry. Spectroscopy, interferometry, and fast photography. A. Magnetic probes. The current, voltage, and magnetic probe data channels all employ analog integrators with 100 or minus 200 pSEC time constants. The magnetic B-dot probes are enclosed in 0.3 centimeters diameter quartz tubes, with typically 2 or 3 probes to a tube. In the straight coaxial version of the apparatus, the magnetic probes are inserted through vacuum fittings that are mounted on the inner electrode, and which allows their insertion depths to be easily changed. In some cases, additional probes are inserted through the outer electrode wall. This is convenient for field mapping when operating parameters are such that the discharge behavior is reproducible. The probe penetrations are generally less than, or equal to half the coaxial electrode gap, except for field mapping of trapped, relaxing toroids in the coaxial expansion volume. These gaps are 7.6 centimeters in the lower gun, 18 centimeters in the coaxial expansion volume, 9 centimeters in the straight coaxial acceleration tube, upper gun, and less than 9 centimeters in the conical gap, for the conical design of Figure 2b. Typically, about 25 magnetic probes are used on any given experiment series. The magnetic probe signals are relayed to oscilloscopes by 20 MHz bandwidth analog fiber optic links. B. Optical spectroscopy. Optical spectroscopy data was obtained using an optical multi-channel analyzer, OLVIA. The system was located inside an TF enclosure. 4 spatial channels of data were obtained via fused silica fiber optic lines. The Jarrell-Ash monospec 27-crossed Chemy-Turner mount spectrograph is stigmatic, so that incident spatial information in the vertical direction, parallel to slit, is maintained through the spectrograph and focused at the exit plane. This capability was used to record 4 spatial channels of spectral data simultaneously. The spectrograph has a turret grating mount, which holds 3 diffraction gratings, any of which can be moved into position without realigning the optical system. The gratings used are 150, 1000, 200, and 1800 lines M&M with 450 nanometers, 400 nanometers, and 550 nanometers blaze, respectively. The grating reflection efficiencies range from 0.1 to 0.9% in the 200 to 1000 nanometers range and are intensity calibrated with known lamp sources. The range, dispersion, and resolution are 25 nanometers, 0.25 nanometers, 2944. Vol. 5. Degnan et al. 2944, channel, and 0.1 nanometers, respectively, for the 1800 line. M&M, grating with a 25 micrometers entrance slit. Entrance slits of 50 and 100 micrometers are available. The silicon-intensified Vidicon detector has a response function that is proportional to a red-enhanced S20 response. The composite system response is absolutely calibrated with known lamp sources. It peaks at 0.08 counts, photon at 430 nanometers wavelength, and is above 0.01 counts, photon from 330 nanometers to 800 nanometers wavelengths. The wavelength versus display channel calibration was done with known lines from Oriel HG, A10E, and KR lamps, and H. Geisler tubes. The OMA software enabled linear or cubic calibration fits using the method of least squares. The wavelength tables of Striganov and Sventitsky were used to identify spectral lines. Comparison of experimental spectra, corrected for composite response function with collisional radiative equilibrium excitation, CRE, predicted spectra was employed to estimate electron density and temperature. This system was normally used with one fiber optic line positioned for axial view, looking upstream toward the first stage gun, and 2 or 3 fiber optic lines positioned for radial view at different axial positions. The same time duration and delay was applied to all positions on a given shot. Thus, for a given shot, only 1 or 2 positions would give data for a usefully short gate duration. Gate durations ranged from 0.1 to 3 MSc. A series of identical operating parameter shots with different ohm gate delays were required to obtain time resolved, as opposed to simply time-gated spectral data. See interferometry. Interferometry was performed primarily with a 5 MW Hine laser of wavelength A equal to 0.633 micrometers. The radial averaged electron density was derived from the plasma-induced phase shift, radians, of a laser beam probing across the diameter of the plasma as it moved axially past observation ports. The electron number density, N, averaged over the probe beam path length 8, is determined by μ equal to 8, NADL equal to 355 times 1012 pod CGS, where P equal to number of passes the laser makes through the plasma. For the results discussed in this paper, P equal to 1, that is Mach, Zender interferometry is used. A single pass means that a full diameter of the coaxial discharge geometry, or 2 coaxial gaps 180 deg apart, are traversed. Previous work, 2628, reported on interferometric measurements of compact toroid formation using Michelson interferometry, for which P equal to 2.28. For the interferometer used in this work, the Hine laser beam was split into 2 nearly equal intensity beams by an 80 MHz Bragg cell instead of the traditional half-silvered mirror. The probe beam passed through the coaxial chamber along a diameter. The reference beam passed the chamber approximately 1 meter to one side. The path lengths of the probe and reference beam to an array of relay mirrors, where the 2 beams are combined and focused onto a fiber optic relay, were approximately 20 meters. The 30 meters long fiber optic relay carries the interfering beam to an RF enclosure. The reference beam is frequency shifted 80% MHz at the Bragg cell, so the interfering beams produce an 80 MHz amplitude modulated beat wave, which is phase shifted by an amount equal to the plasma-induced phase shift of the probe beam. This beam is detected by a photodiode and amplified, 50 to 75 dB. The signal is RF mixed with the Bragg cell driver frequency with and without a quarter period delay to obtain the phase signal in quadrature. These signals are recorded on fast and slow time sweeps, the fast on the timescale of the compact toroid formation and acceleration, for example, 20-second sweep, and the slow to confirm the maximum signal amplitude at the time of interest. This interferometer has been used to observe the radial averaged electron density versus time at a given axial position for trapped, relaxing toroids in the coaxial expansion volume and for moderately accelerated toroids beyond that expansion volume. In the latter case, assuming constant axial velocity and azimuthal symmetry at the axial position of the probe beam enables an estimate of the total electron number in the passing toroid to be made. This can be used to estimate the toroid mass. If one can deduce the average ionization state from time and space, resolved spectroscopy at the probe beam position. D. Microchannel plate camera. Gated microchannel plate MCP. Cameras were used to determine the spatial and time resolution of visible light emission from early time ionization and evolution of the CT plasma. The cameras used ITT F4111 MCP tubes with an 18 mm diameter sensitive area. Several different lenses were used during the fielding of this diagnostic. A Questar 3.5 Maksutov Cassegrain catadioptic type lens with 89 mm aperture and 1300 mm f, 4.6 effective focal length. A Tokina 5250 mm at KF 4.5. 6. Zoom with a Vivitar doubler lens and a Canon 50 mm lens. A Polaroid film pack was set against the MCP sensitive area phosphorphase, and 665/80 ISO film was used for retrieval of both a photographic positive and negative. 1 to 3 cameras were used, as appropriate, in order to fully investigate the early time evolution of the plasma and the injection of gas into the gun. The gate pulse width, trigger time, and gain response were varied in time according to experimental conditions. The disadvantage of using this type of camera is that only 1 image could be acquired per camera during each experiment. Both negatives and positives of MCP images were digitized using a black and white Pulnix TM20 CCD camera with a Sigma 35-100 and 35 MNF 4.5 zoom, macro lens, or a Fujica 25 MNF 1.4 with a 10mm extender ring. The digitized images were processed for optimal visualization of the data and for appropriate correlation with other experimental and theoretical modeling data. 2945. Phys. Fluids B. Vol. 508. August 1993. Degnan et al. 2945. E. Fast framing camera. Fast photography was obtained using a Cordon Model 200 simultaneous streak framing camera. The Cordon rotating mirror camera takes 24 frames, 0.7.9, in. Recorded on Polaroid, Type 55 or Type 57, or cut film, Royal X-Pan. The Cordon camera speed can be varied from 10,000 to 100 RPS, corresponding to mirror periods of 100 to 10,000 musec, and frame exposure times of 128 NSEC to 12.8 MSE. For the experiments reported in this paper, the frame exposure times ranged from 200 NSEC to 1 MSE. The camera view of the coaxial gun was axial via a single overhead mirror or via an interior conical frustum exterior cone overhead mirror array. The multiple mirror scheme enabled monitoring of azimuthal luminosity symmetry of the discharge with a tangential view of both inner and outer electrodes. For those shots in which the Cordon camera was used, the camera provided the first trigger, referred to as the to-pulse. This to-pulse is generated when the mirror reaches a preset speed and repeats every mirror period. The mirror period does not perceptibly change for many tens of periods. The first to-pulse is used to trigger the magnetic field injection and a long trigger delay generator that is typically 11 MSE. The long delay generator output pulse is used to enable a subsequent pulse generator, which is triggered by the next to-pulse. All subsequent timing and triggering is relative to this. This subsequent timing includes the gas puff to formation discharge delay, which is typically 0.7 to 0.8 MSE. This scheme enables timing of the main discharge relative to the camera mirror position with a precision of one camera frame. Simpler schemes also work, but with timing imprecisions of +5 or more camera frames. Fifth, time-dependent numerical simulations. To help understand fundamental CT physics, design experimental hardware, interpret experimental data, and investigate new applications and scaling to different parameter regimes, dynamic computer simulations are performed with Mark II. This code solves the time-dependent, single-fluid, multi-temperature, non-ideal radiation MHD equations on a 2D mesh that is composed of arbitrarily shaped quadrilateral cells. A patchwork of logically rectangular collections of cells, which are called blocks, can be made to form an image of the cross-section of an axisymmetric experiment. This multiple block structure is ideal for performing numerical simulations of complex experimental configurations such as Marauder. The code is an arbitrary Lagrangian-Eulerian, ALE, code that computes the time evolution of all three components of the velocity and magnetic vector fields that are fundamental to MHD. Finite differences are computed with a finite volume technique, and a second-order, accurate Van Leer convection scheme is used. Magnetic field advection is accomplished via the flux-conserving constrained transport algorithm of Evans and Hawley that has been generalized to work on non-orthogonal meshes in an ALE code. For a magneto, fluid of mass density, P, moving with velocity, U, in the presence of a magnetic induction, B, the code solves the fluid momentum equation, dP plus JXB. The mass continuity equation, dP dt plus PV, U equal to 0. The ion energy equation, dPdIV equal to PV. Das15 x bu, the ion energy equation. The mass chive, a P plus Vt, a flux limited, radiation diffusion, d4. Where dt represents the usual convective derivative, and the radiation energy density and the temperature of the radiation field are related by Stefan's constant, ER equal to A, and the magnetic induction equation, AV Vxa. The electric field, E, is obtained from a generalized Ohm's law, EJ UXB plus JXB VP ECN 2N, The displacement current is assumed to be relatively small, so the current density is simply Vxb 140. This set of equations is closed by equations of state for the electron and ion pressures, PET, equal to P, T, where T, N is the electron, ion, temperature, and by models for the various transport coefficients. The K are diffusion coefficients for the thermal conductivity and plasma opacity. The plasma resistivity, N, is related to the applicable collision frequency, MV, N. The electron number density, Ne, depends on the mass density and the mean ionization state, which itself is a function of P and T. The code uses either analytic models or Larnell sesame tables for the equation of state and for transport coefficients. The total pressure, P, is the sum of the ion and electron pressures. Small changes to the temperature are related to small changes to the specific internal energy by a specific heat to equal to C, T. Dtan and P are, respectively, electron-ion and electron radiation coupling terms. The simulations have no model for shear viscosity. The code 2946. Phys. Fluids B. Vol. 5. No 8 August 1993. Degnan et al. 2946. Includes an artificial compressional viscosity, but it is not used in the present non-Lagrangian simulations. The simulations of the Marauder experiment take place on a dynamic adaptive mesh of cells that are concentrated in regions with relatively steep gradients in the magnetic field. A time-dependent self-consistent 2 to 100 RLC circuit model is used to compute the formation and acceleration current waveforms. Solutions to the dynamic equations, LL, 16, are strongly influenced by the boundary conditions which are applied to the mass density, the various transport coefficients, the three specific energies, the components of the magnetic field, and to the components of the velocity. The electrodes are assumed to be perfect conductors on the 10 to 100 pSEC timescale of the relevant experiments and simulations. Thus, magnetic flux that has diffused into the electrodes on the MSE timescale of the bias field coils is assumed to be frozen in the electrodes for the entire duration of the numerical simulation. In steady state, a Hartmann layer would form at the plasma gun electrodes, and its thickness relative to the electrode gap would be determined by the plasma viscosity, the plasma resistivity, and the magnetic field. Although there is no shear viscosity in the simulations, a shear layer at the walls is accomplished by applying a no-slip condition to the velocity field at electrode surfaces. The grid is made sufficiently fine to resolve the boundary layer at no-slip walls that are threaded by magnetic flux lines. Simulations of the Marauder experiment have been performed with H, N, AR, KR, and 10E. In this paper, only the relevant results with AR are discussed. The initial bias magnetic field and mass density distributions for all of the time-dependent MHD simulations are shown in Figs 3 and 6, respectively. The simulations reported herein begin with between 1.5 and 1.6 milligrams AR in the formation gun, distributed, as shown in Figure 6, with the remainder of the simulated volume set to a vacuum pressure of 1.8 x 10 to 4 torr, or between 1 and 2 orders of magnitude above the experimental vacuum pressure, but still sufficiently rare to be of negligible importance to the dynamics of the numerical simulations. The initial mass density in the calculations ranges between 3 times IO, GM-CM, 3, and 1, 10 M6 GM-CM3, 4.5 times 10 to 1.5. LOA heavy particles, CM3, and is chosen to be at 0.05 EV temperature. The Sesame ER table 5172 does not contain values for the pressure at mass densities below 1, 10 M5 GM-CM3, and the opacity table 15170 does not contain opacity and mean ionization state data at temperatures below 1 EV and at mass densities below 1. And therefore, auxiliary pressure and mean ionization state tables were constructed by us to include reasonable values at low densities and temperatures. Local thermodynamic equilibrium was assumed, and the Saha equilibrium equation was used to compute a mean ionization state as a function of mass density and temperature. Strictly speaking, Equilibrium models are not appropriate for these densities where some atomic rates are long compared to the hydrodynamic timescales of particular interest. However, the details of the atomic physics are not. Fig. 9. Heavy particle number, density isocontours, left, and toroidal magnetic flux lines right, from an MHD simulation before relaxation to a Walcher-Taylor equilibrium state. There are 9 density contours that are logarithmically spaced, 2 contours per decade between A at 5 con 10 cm and I at 5 + 10 cme3. There are 7 contour levels for BS, linearly spaced between 0.1 and 0.7 trillions. Of critical importance to the dynamics of the low D plasmas that are simulated. Furthermore, the equilibrium, albeit time-dependent, temperatures and ionization states that are computed by the code are consistent with experimental measurements. An analytic opacity model for low-density argon was also implemented. This model is based on extrapolating the results of post-EF approximately 1, is used to compute the radiative cooling of the argon plasma in the thin limit. Toroidal magnetic flux is injected into the simulation domain by a time-dependent current that is applied as a boundary condition at the bottom of the formation gun. The current ionizes the initially neutral gas, and magnetic pressure pushes the plasma and its embedded bias poloidal field upward toward the expansion volume. A bubble of mass and poloidal magnetic flux is pushed from the gun into the expansion volume. This is illustrated in Figure 9, where a contour plot of the heavy particle number density is shown on the left, and isocontours of the toroidal component of the magnetic field are shown on the right. These 2 snapshots are from a Mach 2 simulation 6 PSE after the beginning of the formation discharge. This is a simulation of a typical shot in which 0.27 mJ is stored in the formation capacitor bank, with the current waveform. 2947. Phys. Fluids 8, Vol. 508, August 1993. Degnan et al. 2947, peaking at 2.388 megaamperes 3.2% 5 seconds after the beginning of the discharge. The energy content of the initial bias field in the formation gun is 388 J. Subsequently, on a time scale that is faster than the classical diffusion time, the magnetic bubble relaxes towards a WT state. This is accompanied and largely preceded by the reconnection of magnetic field lines to form a CT. Reconnection is a complicated 3-dimensional process that is beyond our ability to compute accurately and completely at this time. A number of factors influence the process of reconnection in these axisymmetric computer simulations, including the motion of the plasma, the magnetic and hydrodynamic boundary conditions, the value of the plasma resistivity, and the resolution of the computational grid. A characteristic timescale for reconnection can be obtained from the plasma resistivity, 1, and a characteristic reconnection length scale, VNO. The motion of plasma in the formation gun is not simply laminar. Plasma is reflected from the gun walls and moves toward the reconnection region in a way that maintains at values that are small compared to the width of the gun. Spontaneous reconnection is not simply a result of resistive diffusion, which tends to increase I, competes with the JXB force that arises during reconnection, and that tends to decrease. The large relative motion of various parcels of plasma in the magnetized plasma gun is a product of the resistive tearing instability that tends to decrease and allows the system to evolve on a faster, alphin, timescale than the generally slower diffusion timescale. This point of view is consistent with that of a number of authors, including Axford. Almost any amount of resistivity allows a reconnection to take place in the simulations. We have found that the simulations best agree with experimental data if a phenomenological microturbulent-based, anomalous resistivity, that is a strong function of the local plasma mass and current density, is added to the classical plasma resistivity. Specifically, a Chodura model, 2.53, is used for which the saturated value of the microturbulent collision frequency is given by -101 CXP. Here is the ion plasma frequency, dE is the electron drift speed, is the ion acoustic speed, and A and B are phenomenological constants. This model has been employed previously by Milroy and Brackbill 24 in their numerical studies of field-reversed theta pinches. The anomalous plus classical resistivity is supplemented by a vacuum resistivity that is applied in low-density vacuum cells to yield a function that has the desired behavior in all the regions of the problem domain. This is called the vacuum plus anomalous plus classical VAC resistivity model. The vacuum resistivity is set to 1.26x 10^2 meters, 1.2% UC 10 cm, or equivalently a magnetic diffusivity of 10 square meters, SEC, which determines the rate at which the magnetic field diffuses through the vacuum. The parameters TERS A and B in the Hodura model are set to 0.01 and 3, respectively. The value for A is chosen to be a factor of 100% lower than that used by Milroy and Brackbill in an attempt to mimic the saturation of the instability that occurs in the presence of magnetic shear. 54. We emphasize that the particular resistivity model that is used is not crucial to initiating the reconnection process, but does affect the time scale on which spontaneous reconnection takes place. Other models for plasma resistivity have been used, and in each case magnetic reconnection occurs, and a CT is formed. The different models, however, evolve on different timescales. In the VAC resistivity case, for example, magnetic field reconnection occurs during the time interval between 6 and 15 MSE, and the magnetic field lines are distributed essentially as they are in a WT state by 9.5 MSE. The purely classical resistivity case, however, behaves differently between 6 and 15 seconds. Magnetic field reconnection is delayed until 9 seconds, and the magnetic structure that is formed in the trapping volume downstream of the formation gun resembles a toroidal magnetic bubble more than a WT state for times less than 12 seconds. The VAC model boosts the resistivity near the reconnection region where the magnetic shear is supported by a strong current sheet. The enhanced resistivity of the VAC model speeds the reconnection rate. A comparison between the VAC and the classical models is illustrated in Figure 10, where poloidal magnetic flux lines at 9 seconds after the beginning of the formation discharge are shown for the two cases. At late times, 12 microseconds, both cases relax toward the same WT state on timescales that are short compared to the resistive decay times. The VAC case, however, relaxes on a shorter timescale than does the classical case and appears to be more consistent with experimental data. Simulated magnetic probes are placed in the 2D MHD simulations, and the simulated signals are compared to the experimental data from real magnetic probes that are placed in various locations in the Marauder CT formation experiment. The experimental data is reproducible and shows little azimuthal variation. Comparisons between simulation and experiment were made for various resistivity models, and the difference between the simulated and the real probe signals was found to be smallest when the VAC resistivity model was used. For this reason, the VAC resistivity model is used for all remaining simulations discussed herein. Experimental and simulated B-dot traces from 3 radial locations, each at the same axial position in the coaxial expansion volume, B3 in Figure 2a, are shown in Fig. 11. The timing and magnitude of the probe traces compare favorably. The close agreement between simulation and experiment of the dynamic behavior, as well as the equilibrium structure, suggests that the code is at least approximately modeling the experiment, and that the experimental magnetic flux surfaces do indeed look like the simulated field lines. Formation is essentially complete 10 to 15 seconds after the formation discharge begins. After formation by a 0.27 mJ discharge, at approximately 20 seconds, characteristic values for the simulated argon CT are N, 2 times 104 cm3, B, 2 times 900, EV, Phys, Fluids B, Vol, 508, August 1993, Degnan et al., 2948, Fig 10. Poloidal magnetic flux lines at 9 seconds for 2 simulations that use different models for the plasma resistivity, pure classical, left, and anomalous plus classical plus vacuum, right, T20 EV. The magnetic energy of the simulated CT is on the order of 15 kJ. The alphin speed is approximately 74 kilometers, SEC, which yields a 2.5 seconds alphin transit time across the 18 centimeters wide flux conserver. During formation, the anomalous plus classical resistivity in the plasma is between 1.7 UC10 and 5.2 UC10 cm, always less than the vacuum value. Beyond 15 seconds, the plasma resistivity in the expansion volume is between 1 and 2 times the classical value of approximately 5.78 x10 m/tm. After 10 to 15 seconds, both the experimental and the simulated toroids decay exponentially with a characteristic decay time of 40 msc. An equilibrium decay time can be computed from the Wt eigenvalue, the inverse of which is a characteristic length scale and the mean value of the plasma resistivity. If the Ct is close to a force-free equilibrium, the electric field is almost entirely supported by the internal Ct currents, that is E equal to J, where J equal to Vxb. If the configuration is force-free, then from EQ, 3 Va ab. If A and are spatially uniform, Faraday's law can then be written as AV at P alpha number thirds, the solution of which is B R Bexp, Ne1 440, if the product Na2 is independent of time. The equilibrium decay time constant is determined by A, which for the Ma. Fig. 11. Experimental data, broken lines, and 2D MHD predictions, continuous lines, of magnetic probe traces at the B3 axial level in the coaxial expansion volume with only a formation discharge. Shown are A, top, the radial component of B, at a position 14 centimeters from the inner electrode, B, middle, the toroidal component of 86 centimeters from the inner electrode, and E, bottom, the axial component of B, at the inner electrode wall. Rauder experiment at 20 msec is 21.02 meters, and by the resistivity, N, which is taken to be the classical value given above at 32 eV, the decay time thus computed is 49 seconds, which is somewhat larger than the time constant obtained from experiment and dynamic simulation. In reality, the temperature, and hence the resistivity, of the CT remains essentially constant on a 40 msec timescale as radiative cooling is balanced by resistive heating of the plasma. The difference between the dynamic and equilibrium estimates of the decay time constant can perhaps be accounted for by a time-dependent A. The MHD code was also used to simulate the response of the CT to an acceleration discharge to investigate its stability under the influence of an external driving force and the effect of the discharge on the reconnection process. 2949. Phys. Fluids B. Vol. 508. August 1903. Degnan et al. 2949. Fig. 12. Predictions of the poloidal magnetic flux lines at 9 distinct times from a dynamic Mark II simulation of a CT formed and driven by a pair of 0.27 mJ discharges, with the acceleration discharge applied 12 msec after the beginning of the formation discharge. The time, in SEC, is written below each snapshot. The reconnection time can be substantially shortened by the application of the second, acceleration, discharge. The power feed for this discharge is oriented so that the toroidal magnetic field of the acceleration discharge pushes oppositely directed poloidal magnetic field lines that link the CT to the formation gun toward each other, effectively making the A of EQ 19 quite small. This is called a driven reconnection. The particular location and orientation of the electrical feed that brings current from the acceleration capacitor bank to the formation gun was chosen based on dynamical MHD simulations of various configurations. The present design accomplishes 3 things. 1. It injects toroidal magnetic flux into the CT gun from the outer electrode, a configuration that is mechanically simpler to build and modify. 2. It injects the acceleration magnetic flux radially inwards, which enhances the driven magnetic field reconnection of the CT self-fields. And 3. It encourages the acceleration flux to remain entirely upstream from the CT and pushes the CT downstream until it stagnates on the top of the coaxial acceleration tube. In contrast, for simulations in which the magnetic flux from the acceleration bank is injected in the axial direction from, for example, the upstream horizontal edge of the expansion volume, the CT tends to lose contact with the outer electrode of the expansion volume, and the acceleration discharge sweeps downstream and leaves the CT behind. Indeed, this behavior was seen in earlier designs of the Marauder experiment. A prediction of the dynamic behavior of a CT under the influence of an acceleration discharge in the straight coaxial geometry of Fig. 2a is illustrated in Figure 12. The 0.27 mJ acceleration discharge is produced by 110 mF, 70% kV capacitor with a total initial inductance of 65 Nh. The acceleration discharge begins 12 mSe after the start of the formation discharge. The acceleration current peaks at 2.2 mA with a quarter cycle time of approximately 4 μsec. Poloidal magnetic flux lines are shown at 9 distinct times between 3.5 and 30 seconds after the beginning of the formation discharge. By 12 mSe, the toroid has relaxed to nearly an equilibrium WT state. The driven reconnection is evident at 15 seconds where the acceleration discharge has pressed the oppositely directed CT poloidal magnetic field lines together near the muzzle of the formation gun. At later times, the CT is pushed downstream by the acceleration discharge until it stagnates against the end wall of the coaxial tube that resides above the expansion volume. The code predicts that the CT is accelerated intact and that the mass that is contained in the magnetic structure at moderate times, 12 mSe, remains entwined with the magnetic field at later times, greater than 16 USC. At t-20 seconds, the CT rebounds slightly from the end wall and is held in the coaxial tube by the acceleration discharge. The CT cell fields resistively decay between 20 and 50 μsec, but the magnetic field distribution maintains its CT character. Simulated radial and toroidal magnetic probes for 2 simulations, with and without an acceleration discharge, are shown in Figure 13. The top 2 panels of this figure display simulated probe signals at the B5 axial position, which is above the expansion, trapping volume, 4 centimeters out from the inner electrode, approximately at mid-gap. The radial probe for the accelerated toroid shows a strong reversal between 17 and 19 μsec at the B5 axial location. This is the magnetic field waveform for a CT moving past the probe, and it is consistent with the poloidal field snapshots at 16 and 18 seconds in Fig. 12. Reversal of the radial field signal is absent in the unaccelerated case. Beyond 20 seconds, the CT is held against the top wall of the acceleration coax by the acceleration discharge, and the radial signal decays towards 0 on a long diffusion time scale. The peak value for the toroidal CT cell field at the B probe at B5 is 0.76, 2950. Phys. Fluids B, Vol 5, Nova 8, August 1993. Degnan et al. 2950. Fig. 13. Simulated radial, left, and toroidal, right, magnetic rubber traces at the B5, top, and B4, bottom, axial locations in the geometry of Fig. 2a. The continuous lines are from a simulation with only a formation discharge, and the broken lines are from a simulation with an acceleration discharge which begins 12 ls after the beginning of the formation discharge. T and occurs at 18 psec the time at which the radial component of the field vanishes. Beyond 18 psec, the CT cell field decreases at B5 as the magnetic axis of the CT, where the toroidal component is greatest, passes the probe. The toroidal field of the magnetic piston that is produced by the acceleration discharge peaks at 22.5 psc at a value of 0.62 trillions. The piston field in this simulation is always less than the characteristic CT self field. In contrast, the CT toroidal signal is quite small at B5 for the unaccelerated toroid because the CT is simply not pushed downstream to that axial position. The bottom 2 panels of Figure 13% display simulated probe signals at the B4 axial location, which is near the top of the expansion, trapping volume 6 centimeters out from the inner electrode. The radial field reversal at B4 occurs at between 16 and 18 psec, approximately 1 pse, before the reversal at B5. This is a measure of the speed of the CT as the probes at the B4 and B5 axial positions are separated by 13.65 centimeters. Hence, the CT speed at 17 psec is approximately 15 centimeters pse, 150 kilometers set, and becomes larger at later times. The radial signal for the unaccelerated case does not change sign, and is substantially stronger at B4 than at B5. The double peak in the accelerated BA probe at B4 shows that the top of the CT reaches the probe at an early time, 625 UHC, but that the magnetic axis of the CT, where the toroidal self-field is largest, is driven past the B4 probe 10.25 psc later at 16.5 psc. The toroidal piston field is again less than the CT self-toroidal field. The toroidal field at B4 for the unaccelerated case simply resistively decays with a 30 to 40 YSEC time constant. Sixth experimental results. An axial view framing photo, 200 NSE duration, of the early stage of a compact toroid discharge is shown in Figure 14. The 60 luminous jets from the 60 gas injection valves are evident. The triple mirror arrangement to obtain optical access includes a conical mirror, an interior frustum mirror, and a plane mirror. Imperfections in the frustum mirror cause some image distortion, but the symmetry is still evident. A series of field mapping experiments was performed with only a formation discharge. During this series, operating parameters were solenoid bank voltage equal to 1.7 kV, solenoid bank to gas valve bank firing delay equal to 11 MSE, gas equal to 100 psia argon, gas valve bank to formation bank firing delay equal to 760 pse, and formation bank voltage equal to 70 kV, and capacitance equal to 110 pf. The operating parameters were held constant for the entire series, and magnetic field probes were inserted into the expansion volume at various radial, azimuthal, and axial spatial locations. During this series of magnetic field mapping experiments, one MCP camera with a Cassegrain lens focused at the region in the formation gun that contains the gas valves. 2951. Phys. Fluids B. Vol. 5. No. 8. August 1993. Degnan. Et al. 2951. Fig. 14. Axial view framing photo, positive, of a compact toroid discharge, and was used to obtain views along the z-axis of two of the 60 valves between the inner and outer conductors. There was a high degree of shot-to-shot reproducibility, so it was possible to gather a set of images illustrating a time sequence from 0 to 3.2 MSEC after formation current delivery. The camera-gated pulse width was 200 NSE per image, and trigger delay was increased by 200 NSEC per mapping shot. Figure 15 shows 4 of the 16 images of this sequence. The sequence shows emission distribution from the jets. Fig. 15. Sequence of MCP images, negatives, taken along the axis showing the early time evolution of argon gas plasma. The upper left is from 0.6 to 0.8 MSE. The upper right from 1.4 to 1.6 SEC, the lower left from 2 to 2002.4 seconds, and the lower right is from 3 to 3.2 sec. Fig. 16. Vector plots of the poloidal field in the expansion volume at 18 seconds, experiment 2D MHD, and equilibrium theory, from the outer to inner conductor changing from broad to very bright pinch regions, and very diffuse as the plasma emission travels up the outer conductor into the expansion region. Preliminary comparisons of the theoretical modelling of single jet mass injection and Mach II MHD modelling of the early time evolution of the experiment show encouraging correlation with this time sequence of MCP images. 55.56. Using 2 cameras with zoom lenses, a set of stereoscopic images was acquired and processed. These images provided added spatial information for the evaluation of early time evolution of both argon and deuterium plasmas. The result of the field mapping series is shown in Figure 16, where the poloidal magnetic vector field at 15 points in the RZ plane has been constructed from probe data at 1820 MSE. Also shown are the simulated poloidal magnetic field values from dynamic MHD and equilibrium WT theory. The 3 sets of data compare favorably. Quantitative comparison between experiment, equilibrium theory, and dynamic simulation is obtained by computing a normalized mean square error from sigma by xp blood, where bx is a measured field component at one probe location and bycode is the value computed at that location, either from equilibrium theory or by the dynamic 2D MHD simulation code. The sum goes over all data points. For comparison to the equilibrium code, the field is a function of A and IFC, CEQ, 9. Optimum values of A and IFC are determined at each time point so as to minimize using the simplex method. The residual minimum for the equilibrium, data, and the MHD simulation data cases is plotted as a function of time in Figure 17. This figure shows that the experiment rapidly approaches the minimum energy state from 5 to 10 MSE, and then remains there for the rest of the shot, as the fields resistively decay. The figure also shows that the experiment and the MHD simulation reach a similar state on the same time scale. There is a broad region between 12 and 32 µsec, during which is less than 15%. The experiment and the time. Phys. 5 August 1993. Degnan et al. 2000. Degnan, the exane, the magnetic structure of a CT in the expansion, trapping volume to the Walcher-Taylor equilibrium state. The solid line shows the deviation between the magnetic field as measured in the experiment and that computed by the dynamic MHD simulation code. Dependent numerical simulation approach the WT state after magnetic field reconnection has occurred. The values of IFC and A that yield the best comparison between equilibrium theory and the experimental data, which is represented by the broken line in Fig. 17, are themselves time-dependent. The preferred flux conserver current, IC, is essentially linear in time, rising from 0 to 250 Ka between 15 and 50 seconds. The preferred time-dependent value of A is plotted in Figure 18. Contour plots of the flux function, computed with the time-dependent Mach 2 MHD code as well as with the equilibrium code for a 21.02 meters, are shown in Fig. 19 at 18 MSE, when the experiment appears to be closest to the minimum energy state. The field profiles produced by the two models in the expansion volume are strikingly similar. The majority of the field lines have reconnected by this time to form a predominantly isolated compact toroid. -1. A sample comparison of magnetic field components between the experimental data for a number of similar shots and the computed equilibrium values at the time of. Fig. 18. Time-dependent value of A that best fits the measured field data for an experimentally formed CT. Fig. 19. The computed magnetic flux function at 18 seconds when the experiment appears to be nearest the minimum energy state. On the left is a snapshot of the poloidal magnetic flux lines from a dynamic Mach numerical simulation. These flux lines are linearly spaced between 0 and 0.87 WB. The poloidal flux decreases monotonically from a peak value at the magnetic axis of 0.056 WB. On the right is the flux function, computed by the equilibrium code with the equal to 21.02 cubic meters. Optimal relaxation equal to 18 µsec, 20.1, for a trapped toroid are shown in Figure 20. The scatter in the experimental data is attributed to shot-to-shot variation and to a lack of complete axisymmetry. When the experiment is run with an acceleration discharge, the CT can be pushed out of the trapping volume downstream into the straight coaxial acceleration tube. Empirically, it is important for the toroid to be close to the WT state before it is driven by an acceleration discharge. If the acceleration discharge begins after x2 reaches 0.2, that is after about 7 seconds, the compact toroid is accelerated intact and retains its characteristic magnetic field signature. If the acceleration discharge is fired earlier, accelerated toroid behavior is less reproducible and less azimuthally symmetric. 2953. Fluids B, Vol. 508, August 1993. Degnan et al. 2953. Fig. 20. Experiment versus Walcher-Taylor equilibrium field distributions as a function of R at the axial B3 position in the expansion. Trapping volume at 18 seconds. The curves are obtained from the equilibrium code and points represent experimental data. B. Solid line and diamonds, by long dashed line and plus signs. B. Short dashed line and squares. Magnetic probe traces and interferometry data at two azimuthal locations separated by 180 deg at the B5 axial location in the straight coaxial acceleration tube for a modest energy acceleration discharge in the straight coaxial geometry, shot 91,891 to 5%, are illustrated in Fig. 21. This figure shows the expected waveforms that characterize moderately accelerated compact toroid field histories correlated in space and time with the initial large peak in the radially averaged electron density. The expected magnetic field traces are a reversing radial field near mid-coaxial gap, an azimuthal field trace near mid-gap that shows an initial peak followed by the piston field, and a monopolar axial field at a radial location between mid-gap and the electrode surface. These features of the magnetic field histories are similar to those predicted by the MHD simulations. Figure 13. For shot 91,891.5, the acceleration bank was configured with a 110 UF capacitance and was charged to 70 kV. It fired 12 seconds after the beginning of the formation discharge. The initial inductance was 65 Nh, and the external circuit resistance was 4.3 meters. The radial averaged electron density versus time, obtained from Heaney interferometry, was measured at the same axial position as the location of the magnetic probe. We believe that the first major peak in electron density is primarily due to the compact toroid, and the later signal is due to electrode plasma. The first peak is correlated in space and in time with the magnetic probe signatures characteristic of a compact toroid. Optical spectroscopy of nitrogen and argon accelerated toroids suggests that the average ionization state is between 4 and 5. This suggests that the toroid electron temperature exceeds 20% EV. Considering the injected gas mass is approximately 1.6 milligrams, and that estimates of inertial mass, based on 2D MHD simulations, is on the order of 1 milligram, the volume averaged electron density for the toroid should be approximately a factor of 2 below the 3.5 pi 105 cm peak radial average density observed here. Axial non-uniformity, possibly due to inertial compression, could explain this. The inertial mass estimates obtained from a 0D slug. Fig. 21. Magnetic and interferometric time history data at the B5 axial position from a dual discharge experiment in the straight coaxial geometry. The magnetic data are displayed in the first 3 rows and are from top to bottom the radial, azimuthal, and axial components, respectively. Data from 2 azimuthal locations separated by 180 degrees are shown side by side. The bottom panel shows the line-of-sight averaged electron number density. Model and from inductance histories that arise from experimental current and voltage measurements are consistent with the interferometry data. A number of experiments were performed with injected nitrogen gas because nitrogen has spectroscopic diagnostic advantages over argon. In particular, nitrogen emits visible lines through N+. Optical spectroscopy of accelerated nitrogen toroids indicates that the injected gas species lines are correlated in space and time with magnetic probe signal evidence for the toroid, and that this precedes carbon and hydrogen lines by approximately 2 seconds. In some shots, hydrocarbon insulators at the breech of the formation gun and in the feed of the acceleration discharge flash, driving carbon and hydrogen downstream until it is deposited on the electrode walls. Caudal view optical spectroscopy indicates that during subsequent shots, the carbon plasma is desorbed from the electrodes but remains. 2954. Fluids B, No. 8, August 1993. Degnan et al. 2954. Fig. 22. Optical spectra illustrating time separation of nitrogen, injected gas, and carbon, presumed contaminant. The spectra were taken in the formation volume, A, above, at 9 to 11 seconds, and B, below, at 13 to 14 seconds into the formation discharge. The 110 degrees Fahrenheit, 60 kV acceleration discharge was fired 89 SEC. In the neighborhood of the stainless steel electrode walls. This spectroscopic evidence combined with consistency of several measures of compact toroid mass and the inertial mass, leads us to believe that the H&C electron density seen via optical spectroscopy is electrode plasma that is not dynamically coupled to the compact toroid. A pair of spectra, shown in Figure 22, display line emissions from a CT in the expansion volume during 2 time intervals. The earlier spectrum, taken between 9 and 11 MSEE, is dominated by nitrogen lines. Later, between 13 and 14 MSEC, after magnetic probe signals show the toroid to be pushed out of the formation volume by an acceleration discharge. The spectrum contains silicon and C lines from contaminants. This suggests that the injected mass, entrained by the magnetic field, is reasonably separated from contaminant plasma. The source of the silicon contaminant is believed to be the Pyrex jackets on the magnetic probes. In Figure 23, inductance L versus time R and the inferred axial position Z of the current sheath versus RIIs shown for the straight geometry of Fig 2a, the inductance L is obtained by integrating the RL circuit equation, Li VR dt. Where is the voltage at the capacitive divider voltage probe position outside of the insulator vacuum interface? The calculated inductance is that between the probe and the current sheath, the resistance is assumed to be 1 meter. This is the series resistance past the voltage probe and does not include the transmission line resistance between the capacitor bank and the voltage probe, which is 3.3 M2. An assumed resistance of 0.5 meters causes a small but observable increase in inductance versus time relative to the 1 meter assumption. The inferred axial position of current ignores the movement in the negative z direction of the position of the return acceleration current path. For the straight coaxial acceleration geometry, in which the acceleration capacitor bank is restricted to less than 400 kJ, this return path motion is believed, based partly on 2D MHD simulations, to be small. Also shown in Figure 23 are predictions from Circuit Solver, slug models, also known as 0D or point model calculations, for the inductance and current position versus time. These predictions are shown for several values of the toroid mass ranging from 1 to 3 milligrams. For this particular shot, the best fit occurs at 2 milligrams for times up to the occurrence of the 2 megaamperes peak of the acceleration discharge, which has a 4 seconds rise time. If the motion of the acceleration current return path were also considered, a model of smaller mass would better agree with experimental data. For 2D MHD simulations, which do consider return current path motion, a 1 milligram mass agrees best with experimental data. The increasing upward slope of both the inductance and current position versus time data are strong evidence of acceleration in this straight geometry. This geometry is optimized for diagnostic access rather than for high-energy acceleration. The average velocity inferred from time of flight from the first axial magnetic probe position beyond the coaxial expansion, trapping volume to the second such probe position, is approximately 200 km SEC, consistent with 2D MHD calculations. These calculations predict a peak velocity of 400 km SEC and an acceleration approaching 1010 xg, where g is the terrestrial gravitational acceleration. A representative set of fast-framing camera images of the toroid plasma is shown in Figure 24. The time duration per frame is 832 nsec, which causes details of variations in luminosity to be washed out. The 2 top frames indicate good symmetry just after formation current delivery and as the plasma moves into the expansion volume. The bottom, 2955. Phys. Fluids B. Vel. 508. August 1993. Degnan et al. 2955. Fig. 23. The top left panel shows the experimental acceleration discharge voltage as a function of time in the straight coaxial geometry for a 110 MUF 60 kV bank charge. Clockwise from the top right are time histories of the circuit inductance, toroid axial position, and acceleration current as predicted by a 0D slug code for various assumed values of the toroid mass, along with the experimental histories of each function. Fig. 24. Sequence of Cordon images showing early time ionization and the effects of acceleration current delivery to argon gas. The top left and right frames are from 0 to 0.832. SEC and 0.832 to 1.664 SE, respectively. The lower left and right are from 7.488 to 8.320 SE and 8.32 to 9.152 MSE, respectively. Two frames show continued favorable symmetry as the plasma is beginning to be accelerated into the straight coaxial acceleration tube downstream from the expansion volume by the acceleration discharge.
Seventh conclusions.
We have formed meter major diameter, 18 centimeters minor diameter, compact toroids using a puffed gas, field-embedded coaxial plasma gun. Toroids in the 1-2 milligrams mass range have been made with a variety of plasma species, with argon and nitrogen being the most thoroughly diagnosed. The toroids relax towards a Walcher-Taylor state, with closest approach to that state occurring between 15 and 20 UC after the beginning of the formation discharge. Time-dependent 2D MHD numerical simulations predicted that the toroids could be accelerated intact, and these predictions were borne out by experiment. The toroids can withstand accelerations in the 100 xg range by an acceleration discharge that begins at a time between 7 and 12 MSE after the beginning of the formation discharge. The toroid material species is the injected gas species. Additional plasma, including carbon, is observed behind the toroid. Caudal view spectroscopy suggests it is concentrated near the electrodes. Both interferometry and an estimate of the inertial mass deduced from the dynamic behavior of the inductance suggest that a large fraction of the injected gas is entrained in the toroid. There is substantial agreement. 2956. Phys. Fluids B. Vol. 5 No. 8. August 1993. Degnan et al. 2956, tween the experimental results, dynamic 2D MHD simulations, and, when appropriate, 2D equilibrium calculations. Experiments are currently being performed in the compression geometry of Figure 2b, and these will be discussed in a future paper. Acknowledgements. The Marauder experiment was motivated by the race effort at Lawrence Livermore National Laboratory. We are indebted to our colleagues at LNL, especially C.W. Hartman, J.H. Hammer, J.L. Edelman, H.S. Mack, Lean, and a W. Molvik for freely sharing their expertise with CT plasmas with us. We also thank J. Buff of Mission Research Corp. For constructing the mean opacity for cold low-density argon that was used for radiative cooling in the MHD simulations. Finally, we acknowledge the interest and support of W. L. Baker and B. B. Godfrey from the Phillips Laboratory, and E. Teller of LNL, H. Alphanin. In proceedings of Second United Nations International Conference on the Peaceful Uses of Atomic Energy, Geneva, Switzerland, 1958, United Nations, Geneva, 1958. Fall 31, p3. R. D. Milroy and J. U. Brackbill, Phys. Fluids 25, 775, 1982, 3. J. L. Schwarzmeyer, D. C. Barnes, D. W. Hewitt, C. E. Saylor, R. I. Shestakov, and R. L. Spencer, Phys. Fluids 26, 1295, 1983. A. D. Milroy and J. U. Brackbill, Phys. Fluids 29, 1184, 1986. M. Tushufsky and R. L. Spencer, Phys. Fluids 29, 3711, 1986. H. Elberk, H. Momota, and T. Tajima, Phys. Fluids 30, 3548, 1987. R. D. Milroy and J. T. Slauv, Phys. Fluids 30, 3566, 1987. W. Armstrong, R. K. Linford, J. Lipson, D. A. Platz, and E. G. Sherwood, Phys. Fluids 24, 2068, 1981. M. N. Rosenbluth and N. Bussack, New CL. Fusion 19, 489, 1979. M. N. Bussack, H. P. Firth, M. Okabayashi, M. N. Rosenbluth, and A. M. M. Todd in proceedings of 7th International Conference on Plasma Physics and Controlled Nuclear Fusion Research, Innsbruck, Austria, 1978. International Atomic Energy Agency, Vienna, 1979. Vol. 3, p. 249. G. C. Goldenbaum, J. H. Irby, Y. P. Chong, and G. W. Hart, in Proceedings of the 9th European Conference on Controlled Nuclear Fusion and Plasma Physics, 17 to 21, September 1979, Oxford, England, Ukiah Cullum Laboratory, Abingdon, England, 1979, p. 129. G. C. Goldenbaum, J. H. Irby, Y. P. Chong, and G. W. Hart, Phys. Reverend Let. 44, 393, 1980. H. Bruns, C. Chin, Fat, Y. P. Chong, A. W. De Silva, G. C. Goldenbaum, H. R. Green, G. W. Hart, R. Hess, J. H. Irby, and R. S. Shaw, Phys. Fluids 26, 1616, 1983. 14. T. R. Jarboe, I. Hennins, H. W. Hoyder, R. K. Linford, J. Marshall, D. Platts, and E. R. Sherwood, Phys. Reverend Let 45, 1264, 1980. J. C. Fernandez, C. W. Barnes, T. R. Jarboe, I. Hennins, H. W. Hoyder, P. L. Klinger, S. O. Knox, G. J. Marklin, and B. L. Wright, New C. L. Fusion 28, 1555, 1988. M. Yamada, R. Ellis Jr., H. P. Firth G. Hart, A. Janos, S. Jardneff Leventon, D. Meyerhofer, M. Mimura C. H. Nam, S. Paul, A. Sperduti, S. von Gola, F. Wysocki, and P. Young, in Plasma Physics and Controlled Nuclear Fusion Research, 1984, Proceedings of the 10th International Conference, London, International Atomic Energy Agency, Vienna, 1985, Vol. 2, p. 535. 17. A. Janos, Phys. Fluids 29, 3342, 1986. 18. W. C. Turner, G. C. Goldenbaum, E. H. Agranaman, J. H. Hammer, C. W. Hartman, D. S. Prono, and J. Tasker, Phys. Fluids 26, 1965, 1983. C. W. Hartman and J. H. Hammer, Phys. Reverend Let. 48, 929, 1982, 30 M. G. J. H. Hammer, P. F. Nowak, C. W. Hartman, J. L. Edelman, G. B. Zimmerman, and J. F. Holzrichter, Bull. A. M. Phys. A. Sock. 33, 1925, 1988. See National Technical Information Service document, number PB, 92,206,168, M.R. Douglas, and others, in Proceedings of the 9th International Conference on High-to-Power Particle Beams, 25 to May, 25, 1992, Washington, D.C., edited by D. Mosher and G. Cooperstein. Copies may be obtained from the National Technical Information Service, Springfield, Virginia, 22161. A. W. Molvik, J. L. Edelman, J. H. Hammer, C. W. Hartman, and H. S. MacLean, Phys. Reverend Let. 66, 165, 1991. R. E. Peterkin, Jr., J. H. Degnan, N. F. Roderick, C. R. Sovinek, and P. J. Turchi, in Digest of Technical Papers, 8th EEE International Pulsed Power Conference, 17 to 19 June 1991, San Diego, CA, edited by R. White and K. Prestwich, The Institute of Electrical and Electronics Engineers, New York, 1991, p. 277. See National Technical Information Service document, number PB 92,206,168, R. E. Peterkin, Jr., and others in Proceedings of the 9th International Conference on High-to-Power Particle Beams, 25 to May 29th, 1992, Washington, D.C., edited by D. Mosher and G. Cooperstein. Copies may be obtained from the National Technical Information Service, Springfield, Virginia, 22,161. K. E. Hackett, W. L. Baker, J. D. Beeson, C. J. Klaus, J. H. Degnan, D. Dietz, J. E. Rowley, C. R. Sovinek, J. Buff, M. H. Friese, R. E. Peterkin, Jr., and N. F. Roderick, in Megagas Fields and Pulsed Power Systems, edited by V. M. Titov and G. Svetsov, Nova Science, New York, 1990, p. 55. J. H. Degnan, B. W. Mullins, J. D. Beeson, M. E. Dearborn, D. Dietz, K. E. Hackett, J. L. Holmes, A. L. Rudin, D. W. Price, C. R. Sovinek, G. Bird, S. K. Coffey, S. W. Seiler, G. F. Q2, R. E. Peterkin, Jr., N.F. Roderick, and P.J. Turchi, in Physics of Alternative Magnetic Confinement Schemes, edited by S. Ortolani and S. Indoni, Societe Italiana di Fisica, Bologna, Italy, 1991. 2007. J. H. Degnan, G. P. Barker, M. E. Dearborn, S. E. Englert, T. J. Englert, J. L. Holmes, F. M. Lair, G. J. Marklin, B. W. Mullins, D. W. Price, N. F. Roderick, E. L. Rudin, C. R. Savinek, P. J. Turchi, D. Gale, J. de Graam, M. Scott, W. Somars, G. Bird, S. K. Coffey, S. W. Sealer, G. F. Q2, and R. E. Peterkin, Jr., Bull, M. Phys, S. Okie. 36, 2458, 1991, E. L. Rudin, B. W. Mullins, M. E. Dearborn, and S. K. Coffey, Phys. Fluids B4, 1800-1992. E. N. Parker, J. Geophys. Res. 62-4-1957. J. B. Taylor, Reverend Mod. Phys. 58, 741-1986. See also Magnetic Reconnection in Space and Laboratory Plasmas. Geophysical Monograph 30. Edited by E. W. Haynes, American Geophysical Union, Washington, D.C., 1984. L. Walcher, in Proceedings of the National Academy of Sciences of the United States of America, National Academy of Sciences, Washington, D.C., 1958, Vol. 44, p. 489. J. B. Taylor, Phys. Reverend Let 33, 1139, 1974, J. B. Taylor, in Pulsed High Beta Plasmas, edited by D. E. Evans, Pergamon, New York, 1976, p. 59. G. J. Marklin, M. E. Dearborn, and S. E. Englert, Bull, Am, Phys. Soc. 36, 2459, 1991. R. E. Rainovsky, W. L. Baker, Y. G. Chen, J. Holmes, and F. A. Lopez, in Digest of Technical Papers, 4th EEE International Pulsed Power Conference, 6 to June 8, 1983, Albuquerque, NM, edited by M. F. Rose and T. H. Martin, The Institute of Electrical and Electronics Engineers, New York, 1983. p. 196. E. L. Rudin, J. H. Degnan, T. W. Hussey, M. C. Scott, J. D. Graham, and S. K. Coffey, in IEEE Conference Record, Abstracts, 1992 IEE International Conference on Plasma Science, 1 to 3 June 1992, Tampa, FL, Institute of Electrical and Electronics Engineers, New York, 1992. Also time-resolved mass flow measurements for a fast gas delivery system, Reverend Cy. Instrom, 64, 1740, 1993. J. D. Graham, D. Gale, W. Somers, M. Scott, and Y. G. Chen, in Digest of Technical Papers. 8th EE International Pulsed Power Conference, 17 to 19 June 1991, San Diego, CA, edited by R. White and K. Prestwich, The Institute of Electrical and Electronics Engineers, New York, 1991, p. 990. J. L. Edelman, J. H. Hammer, and C. W. Hartman, Bull. M. Phys. 1987. H. K. Cambridge University Press, New York, 1978. M. Taguchi, T. Miyazaki, and S. Kaneko, J. Phys. SOC. Japan, 54, 2163, 1985. M. Abramowitz and I. Stegan, Handbook of Mathematical Functions. Dover, New York, 1970. p. 374. S. Izuka, E. Minamitani, H. Tanaka, and E. Kiwamoto, Phys. Reverend Let. 53, 918, 1984. R. Straganoff and N. S. Sventitsky, Tables of Spectral Lines of Neutral. 2957. Phys. Fluids B. Vol. 508. August 1993. Degnan et al. 2957. And Ionized Atoms, IFI. Planum Data Corporation, New York, 1968. See National Technical Information Service Document Number 192,285. Mission Research Corporation Report AMRC R 874 by M. H. Fress, 1987. Copies may be obtained from the National Technical Information Service, Springfield, Virginia 22161. B. Van Leer, J. Comput. Phys. 23, 276, 1977. C. R. Evans and J. F. Hawley. Astrophes. J. 332, 659, 1988. 47 SMA. A Los Alamos National Laboratory Equation of State Database. Los Alamos National Laboratory, Los Alamos, NM, LRO 92, 3407. The Sesame Equation of State, EOS, library is a computer-based library of tables of thermodynamic properties of a variety of materials. It is maintained by the EOS and Mechanics of Materials Group, TI, of the Theoretical Division of Los Alamos National Laboratory. Address inquiries to Sesame Library, T1 MSB 221, Los Alamos National Laboratory, Los Alamos, NM 87545. S1 Brzezinski, in Reviews of Plasma Physics, edited by M. Aliontovich, Consultants Bureau, New York, 1965, Vol. 1, p. 205. D.E. Post, R.V. Jensen, C.B. Tartar, W.H. Grasberger, and W.A. Locke, at Data NewCL. Data Tables 20, 397, 1977. W. Horton and T. Tajima. J. Geofis. Arez, 93, 2741, 1988. 3. W. I. Axford. In Magnetic Reconnection in Space and Laboratory Plasmas. Edited by E. W. Hones, Jr., American Geophysical Union, Washington, D.C., 1983, p. 360. R. Chadora, NewCL. Fusion 15, 55, 1975. R. C. Davidson and Anna Kroll, NewCL. Fusion 17, 13, 1977. M. T. Glad and Anna Kroll, Phys. Fluids 21, 1640, 1986. S. E. Anglet, D. E. Bell, and S. K. Coffey, Bull, Am. Phys. S. O. Cool, 36, 2459, 1991. S. E. Anglet, D. E. Bell, G. J. Marklin, and S. K. Coffey, in Ref. 36, 37 W. H. Press, B. P. Flannery, S. A. Tukolsky, and W. T. Vetterling. Numerical Recipes, Cambridge University Press, Cambridge, 1986, SE 1024. T. J. Englet, G. F. Q2, and S. Vigil, Bull. M. Phys. Sook, 37, 1474, 1992. M. E. Dearborn, D. E. Bell, J. H. Degnan, J. F. Q2, R. E. Peterkin, Jr., and E. L. Rudin. Mass Estimates for Deuterium Compact Toroids, submitted to J. Apple Phys. 2958. Phys. Fluids B. Vol. 5, No. 8, August 1993. Degnan et al. 2958. Copyright 2003 Ebiesco Publishing.